So my objective today is I want to do a real quick half-hour lecture just to get far enough into the HDL stuff that you guys can start lab 2. If you're still working on lab 1, you can do that until Sunday. Are you guys done with, you all done with lab 1? Okay, good, cool. Okay, so last time in my lecture on Monday I was talking about HDL. I gave kind of a background of HDL and where it came from and what it means and the different HDL languages and how it's used. And so in this lecture, I'm going to get a little bit more specific about syntax. So here's an example where we have 3 modules defined. One is called AN3, we've got one called inverter, and one's called NAN3. Normally these would be in 3 different files. You can put them all in one file, but the convention is to have each module in its own file like you would a Java class. The problem is that, as I mentioned on Monday, these files form a design hierarchy. But if you just have the files, you have no idea what the design hierarchy is. Because there's nothing in the files or the names of the files that imply what the hierarchy is other than the internal contents of the structure, right? So looking at these files, like for example, if you go to GitHub and you download a hardware design that has 100 Verilog files, you're not going to know which one is the top level file and which ones are the leaf files. Like you don't, so you have to, unfortunately, the only way to do that is to look inside. And you can see that the AND gate and the inverter are both behavioral code. They just have an assign statement. They don't instance any other modules. So these are leaves, right? These are the bottom of the design tree. Whereas the NAND gate instantiates both the AND gate and the inverter. So this is the root, right? This is the top level design. But again, you have to figure that out, right? So what this is doing is creating a top-level design called NAN3 that has top-level inputs A, B, and C and top-level output Y. That's the pinout, right? Now on the FPGA, if this were the top-level design on the FPGA, the root of the design tree, all of these inputs and outputs would have to match the exact names of pins on the FPGA, right? To actually connect these two things outside the chip, right? Whereas everything underneath there could be arbitrary, right? So then, so I got this thing called NAN3, so it creates this, basically like this symbol. And then I'm going to instantiate an AND gate and an inverter. The syntax here is kind of similar to what you're used to. You start out with AND3, which is the module name, and then you've got AND gate, which is the instance name. This instance name is basically not used for anything, except for when you simulate, it shows up as the AND gate in the simulation. So the simulator will create a design tree, a design hierarchy, and it will use those names in there, but they don't actually translate to anything in the physical target, the implemented design, right? These are only there for human purposes because when you synthesize it, it gets flattened, all the hierarchy gets flattened out. Okay, so then, so I've got an AND gate and an inverter, and I've got also declared this thing called N1, which is a logic. This is a single bit wire. It's meant to be an internal signal. It's not connected to the inputs and outputs, it's just internal. And then my goal is so I've got 3 lines of code in here, and so that creates these 3 things inside the AND gate, and now the goal is to wire everything up. So the way they're wired up is it's done through these what are called port maps, parentheses after the instances. And the syntax here is each port is specified as dot and the formal port name, which is the name inside the thing that you're instancing. So in this case, the AND gate is going to have .A, .B, .C, and .Y because those are the ports there. And then after the dot port name, you have parentheses, and that's the actual signal in the current level of the hierarchy you want to connect. So in this case, I'm going to connect the A input of the AND gate to the global input A, the B port to the global input B, and the C port to the global input C, but the Y output I'm going to connect to the N1, right? So that'll connect the Y to the internal signal. And then on the inverter, I'm going to connect N1 to the A input, and I'm going to connect the output of the inverter to the global output. When I say global, I mean the inputs and outputs of the NAND gate, right? So, yes?
It has nothing to do with the order that you put them up.
No.
You could have connected up the Y output of the inverter to say A instead of having the A port, and then you'd have A naught
Yes.
going into the and
Exactly.
the Y would go out.
Exactly. Yeah, I could have connected that output of Y to this A. Yeah, sure. Yeah, but the signal, but in order to do that, you would have to use an internal signal like this N1 to do that, to serve as the connection point. Okay, so basically that just creates correspondences between the signals in the AND gate with the ports on each of those two modules that I've instantiated. Now the problem with this is, you might say, well, that's pretty straightforward, except the problem here is that it creates this situation now where the Y wire inside the NAND gate and the N1 wire inside the NAND gate and the A input inside the inverter are all the same wire, but they have different names at different levels of the hierarchy. So this can become confusing because, as I mentioned, when you synthesize this, only one of these names will remain for that wire. The other ones will get dropped out, right? But inside the design, you have these three different names. So if I drill down into the NAND gate and I force the Y output to be something, that force will also force the N1 signal here and the A signal in there to be the same thing, because they're all the same wire. They just have different names depending on what the context is, which design you're inspecting them in, right? Okay, so then I mentioned all that. Okay, so also I mentioned this logic type. So logic is, if any of you have seen Verilog before, logic is the type in SystemVerilog that has replaced the wire and reg types in Verilog, right? So logic basically just means it's a bit, but it's a four-state bit that includes the X and the Z values that are used for simulation purposes, right? So if you want to have a multiple bit signal, then you create an array of logics, except the way you do that is really bizarre and different from every other language. You say logic and then bracket, for example, 3:0 bracket. So that'll create a 4-bit array. And then this array is applied, these array bounds are applied to A and B. Okay, now what's weird about that? Well, first of all, in every other language that I have ever seen, yeah, I think so. Every language I've seen in my 40 years of programming has put the array bounds after the variable name, not before. So this is totally unique to Verilog. Also, why not just say 4? Why say 3:0? Why give so basically you're giving the number of the most significant element index, colon, and then the number of the least significant element index. And in order to figure out how many bits that is, you have to subtract them and add 1 because it's inclusive. So I have to do the math in my head. Okay, 3 minus 0 is 3, plus 1 is 4. Oh, it's 4 bits. Why not just say 4? Unclear. Now you might say, well, wait a minute. What if you put 0:3 instead of 3:0? Does that reverse the order? No, has no impact at all. But the convention is to put the bigger number first. Now, one nice thing about doing that, though, and I think the reason why they did it that way, is because this type, logic 3 down to 0, is being applied to both the A and the B because I didn't specify a type for B. Right? Now, I do specify a type for Y1, which is the next thing in this list, right? So what ends up happening is that A and B are 4 inputs, and then these 5 output values, Y1 through Y5, are all going to be 4 input output values, right? That makes sense? Now, you don't have to do it. This is a shorthand. You could specify logic 3 down to 0 for B as well. And some people would prefer to do that because it's more clear, right? That some people like to write code in a way that's easier to read and more kind of self-documenting. So in that case, you may not want to put all these guys on the same line. You may want to specify the type for each, and that's fine. You'll notice if you look in the wrapper files that we provide for Lab 2, that that's how we did it, because the grad student I had that wrote those was very particular about how he coded. So his code is very, is written to be as clear as possible. So he doesn't use these tricks, these shorthand tricks, okay? But anyway, yeah, so those are just all 4-bit signals, and if you simulate them, you'll see that there's 4-bit values for each, right? Okay, another thing that's very common in Verilog is this ternary operator. So the ternary operator is available in Java and C. I don't know if you can do this in Python, but basically the idea is you have a condition followed by a question mark, right? And then whatever comes after that question mark is what the whole statement or the whole expression evaluates to if the condition was true, and then you have a colon, and then you have the false. So this is something that you have the value that it evaluates to if the condition was false. So this is something that is available in C and Java, but hardly anyone ever uses them. They're very obscure and rare to use in those languages. But in Verilog, it's very common because this creates a multiplexer, right, in the hardware. So if you have, in this case, I have assign Y equals, I check S, which is the condition. In this case, this condition is going to be the select input on my mux. And then the two values on either side of that colon are going to be the inputs. The only thing that's confusing here, though, is that because I didn't say S equals 0 question mark. You could say that. You could say S equals 0, right? And if you do that, then the 0 select would correspond to the first input listed, right? So because I didn't put an equals here, in other words, this mux is a little confusing because the first clause here, D1, is actually going to be the second input on the mux, the 1 input. You guys with me on that? But anyway, the point is that this is an expression you can use to create muxes. And in your CPU, muxes are fundamentally what's used to create data paths in your CPU. This is how, for example, you can choose between writing the output of the ALU into the register file or writing the output you're loading from memory into the register file, right? That's a mux that controls that. Likewise, you have an ALU where the second input on the ALU can come from the register file or it can be an immediate, right? How is that determined? With a mux, right? So your CPU is basically going to be formed of these muxes with control signals from the control unit controlling the muxes. And this is what allows you to kind of steer data around and create data paths for each instruction. Okay?
Can I state that to see
Sure.
if this is true? I assume that if S was 1, that was true, and therefore you do the true.
Right. So if S is 1,
that's true, and you do D1.
then I'm going to take the second input. I'm going to take D1, yeah. And I'm going to take D1 and I'm going to send that to the output. And if S is false or 0, it's going to be D0. What I was saying though is that this style is, I got this slide from the book, but I don't like this style. I would have said if S equals 0, because that way this would have been my D0 and that would have been my D1, right? So because normally muxes are assumed to have the 0 select would be top and the 1 select would be bottom.
What if you have a multiple? The mux has more than the 2, so it's a 2-bit select.
Sure.
How would you write that?
You can do that. You end up using a nested. You would nest it. So in the false part, you would have another ternary.
If then.
Yeah. If then else basically. So you can do that. Of course, at the end, you always have to have the default with just colon. Okay. All right, so this example is a full adder with propagate and generate logic. This just demonstrates that you can have two intermediate internal signals in here and assigns that assign them, and then two other assigns that drive the outputs, right? Now this is an interesting example because this illustrates why Verilog has what they call concurrent semantics. Because what's happening in here is that if the inputs A or B change, it causes a triggering event that updates P and G. And then if those change, it will subsequently trigger these two other assigns that depend on those two guys, right? But you can take these 4 lines of code and scramble them in any order, and it won't change the behavior of this module because each of these 4 assignment statements are set up as triggers. Anytime their inputs change, the outputs are updated, regardless of what order they're in this file. Does it make sense? Okay, so so then operators, we have operators that you're familiar with. We have tilde, which is shown here as not. It's a complement, or it's a logical complement. If it's applied to a multi-bit logic signal, then it's a bitwise complement. We have multiply, divide, and mod. Now these are interesting because you pretty much will never use these in synthesizable Verilog. You might use these in test code that's part of a test bench. But if you're doing a multiplier in code that you want to put in logic, you're probably not going to rely on the synthesizer figuring out how to implement that multiply, because there's a lot of ways you can build a multiplier, and there's a lot of trade-offs you can make in a multiplier design. You know, resources versus latency. You know, basically time, the performance versus the cost. Right? There's different multiplier designs. So you would probably never put a multiply, divide, or a modulo in Verilog code, in synthesizable Verilog code. But like I said, you could put it in test code that you just intend to simulate. But add and subtract that's usually pretty reasonable. Oh, by the way, we do use a multiply though in the ALU we use for this class, strangely, but it just seems to work out for us. So, for this class, because we're running at a low clock rate and we have plenty of FPGA resources. So we do use it actually in this class to synthesize. I did try divide though, and that never worked because that like ate up the whole FPGA when I did that. I tried to create a single cycle divide in the ALU, and it was too expensive. Something I hope to fix one day. Anyway, then there's shift, regular shift, logical shift, and arithmetic shift. Arithmetic shift propagates the sign bit for if you're dealing with sign numbers. You might say, well, wait, why does that? You can't do that in C and Java. Yeah, that's correct, because C and Java can distinguish between logical and arithmetic shift based on the data types that you're shifting, whereas in this case, we're shifting logic, right, which, unclear if that should be treated as signed or unsigned. So we have these arithmetic shifts. Then you've got comparison, equal, not equal. Now, the equal, equals, and bang equals also have counterparts that are equals, 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 and bang equals, equals. The difference is that these are intended to be synthesizable, which means that if you have two signals in your simulation that are both Z, which are high impedance, and you test them for equality, if you use this equals, the answer is false. So if you say Z equals equals Z, false. They're not equal. And the reason it'll do that is because in real hardware, you can't compare two floating signal values in digital logic. It's impossible. However, if you use equals, 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 and then you say Z equals, equals, equals Z, that'll be true, because that one is designed for simulation purposes where it'll allow you to compare two non-binary values. You can compare X's and Z's for equality and it'll work, but only if you use the equals, 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 right? On the other hand, if, in fact, let me rephrase that. Actually, that's wrong. If you use equals, equals, and you put Z's in there, actually you won't get false, you'll get an X. Sorry, it'll be non-determined, right? So in the simulator, if you say Z equals, equals, Z, or X equals, equals, X, either way, the answer will be X, right? Meaning I can't compare these because I can't compare, I garbage in, garbage out. You're putting floating signals in, there's undetermined value out. But if you use equals, 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 then it'll be true if you have two Z's. It'll act like a programming language would if you compare two equivalent values, right? You guys with me? So yeah, sorry, that's the difference. I don't know why this is from the textbook, and I don't know why the textbook didn't list those special equality symbols. And then we've got, your bitwise NAND, and NAND, XOR, XNOR. XNOR is a little weird. Oh, also NAND is a little weird. This is not available in C or Java. You can't say tilde ampersand, right? But this is the actual operator in Verilog. Likewise, tilde bar is NOR. That's kind of cool. And then, of course, the ternary. And ternary is the lowest level of precedence. Okay, so when you specify a number in Verilog, you should specify the width. You don't need to do this in Java and C because, again, you have a data type that specifies the width. So if you declare something as a long in C, then it's 32 bits, and long is 64 bits. But in this case, we don't often, it's better to specify what the bit width is. So you would say the bit width apostrophe gives the bits, and then B, H, D, or O, which is the the base. So H is hex, O is octal, B is binary, D is decimal, and then the number. So for instance, 8'B11 is saying this is an 8-bit value with the binary value 11. So in reality, you're going to have 6 zeros followed by 2 ones, right, inside that binary value. Makes sense? Because it's going to automatically put the 0 padding in there, right? Because obviously 3 only requires 2 bits, but I want to store that in 8 bits. You can also use underscore, which is ignored by the compiler, but it's useful for separating, bit fields if you have a number with different bit fields. Now, if you don't put that and you just put the number 42, the default base is decimal, which is pretty common in programming languages. But then you're leaving it to the compiler to figure out what the width is, right? And sometimes that works, and a lot of students in the class do that. They'll just put a number. I haven't seen, I don't know if I can remember any times that caused an actual bug. But generally when you're designing hardware, you should try to be, careful with that. Okay, so a lot of times in code, it's common in Verilog code, you want to manipulate bits. So one of the ways to manipulate bits is to concatenate different bits, different values, different binary values into a larger signal. So for that, use this curly brace notation. So you put curly braces around all the things you want to concatenate and use commas to separate them. So in this case, I want to assign y to have different components in it concatenated. The first one is A2 down to 1. So this is an operation where I'm slicing out bits 2 down to 1, right? And then I'm going to concatenate that with, this is a duplication operator. So this is going to take bit 0 of B and it's going to duplicate it 3 times. Notice that there's 2 layers of curly braces here. You have to do that. You have to use exactly that syntax if you want to use the duplication. So it has to be curly brace, duplication number, then curly brace, then what you're duplicating, and then 2 curly braces at the end. So you can't leave any of those curly braces out. And then this is bit 0, and then this is going to be a constant 6 bits binary 100010, and then again that underscore will be ignored. So this will end up creating a 12-bit value. If you add up all the bits there, there's 12 bits. Okay. Now one of the things I learned within the past just few years is that you can actually do that same thing on the left-hand side of an assignment too. So you can take something like y, and you can assign it to, in this case, it's going to assign 2 signals from y, A bits 2 down to 0, and B, right? So in this case, y is assumed to be 3 bits, and I'm going to take one of those bits and put it in the least significant bit of B, and the other 2 bits will be in bits 2 down to 1 of A. Somebody asked me on Wednesday, what would happen if y is 4 bits and you did this? I'm not sure. I think it probably would just use the least significant 3 bits, but again, you want to be careful. If you do that, you're leaving the result of that up to the compiler. Sometimes you'll get an error, or sometimes you may get behavior you don't expect. So, if y is more than 3 bits, then you can just slice it here, right? You could say y 2 down to 0 here, right? Does it make sense? So, but yeah, I'm not sure exactly what would happen if y is, or if y is 2 bits for that matter, and you did that. Okay, so here's an example where you would use the duplication operator. This is a sign extension, so we're going to take B. In this case, I'm assuming B is like a 16-bit value. And then I'm going to take the sign bit, which is B bit 15, and I'm going to duplicate it 16 times, and then concatenate that to B. So that will sign extend. It'll turn B from a 16-bit value to a 32-bit value, and it'll sign extend. It'll take the sign bit and use that to fill in the other 16 bits. The reason I bring this up is because we have to do that in our CPU design. And also, the way I used to do it is this. I used to copy and paste the sign bit 16 times before I knew about the duplication operator. So, I mean, both of these are legit, except obviously this bottom one, easier to read. Okay, I'm going to skip that. Another thing I'll point out, just in case you guys ever see it, we probably won't need this for this class. There's this thing called a reduction operator, which is where you can take a multi-bit signal in Verilog and you can reduce it to a single bit. So for example, in this case, if you say ampersand A, that's not address of A like it is in C++. What that is it's going to take all the bits of A, in this case 8 bits of A, and it's going to feed them into an 8 input AND gate, producing a single bit output. So AND A, of course, will just be 1 if all 8 bits of A were ones and 0 otherwise, right? And this is, it's equivalent to writing this. I've never needed to, I don't think, I might have used it actually a few times, but it's kind of obscure. Okay, so then so that's kind of the basic Verilog syntax. I want to switch topics real quick to simulation. So as I mentioned on Monday, we have a simulator called, what's it called? QuestaSim, thank you. Drawing a blank, getting old. QuestaSim. So it used to be called Model Sim, and then they changed the name. But QuestaSim is an industrial strength simulator. It's what they use. It's that, and Synopsys has one called vSim. But those are the two sort of most well-known simulators. They're commercial. We can use them. We get they give us an academic price, so they kind of give it to us for a cheap, annual license. But normally they're pretty expensive, and they're designed for simulating huge systems, huge circuits. They're way overkill for what we do in this class. Super overkill. But we use them just to, to give you some exposure to industrial strength tools. But it's almost laughable how much more capable they are than what we use them for in this class. There are open source alternatives for this, namely Verilator and Icarus Verilog. However, those are even harder to use in Model Sim. And Icarus doesn't support SystemVerilog, so we can't use that. And Verilator only supports two state logic. So a logic signal in Verilator is just a 0 or 1. It doesn't have the Z or X, which means if you double drive a signal, you won't detect it by running it in Verilator. They do that for performance reasons, I think. Because in order to implement 4-state logic in C would be very expensive and slow. But the problem is that it doesn't make it really suitable for debugging things. So if you double drive a signal, you may not know it for a while if you're using Verilator. So anyway, but QuestaSim is still kind of antiquated. You'll find that the interface is really the same as it was 35 years ago. They're using the old, I think this is called the widgets API. So it predates like all the modern GUI APIs for Unix, like GTK and SDL and Qt and all that stuff. This is built on like the original X Windows widgets, X widgets, I think it was called. So it's really kind of cumbersome to use. But if you can start it up with vSim, and you'll see this, and basically what this is telling you is that you have no design loaded, right? So the first thing you want to do is load a design, and so you have to actually compile your design first, which I showed you on Monday when I demoed this. You can just use the vlog command to compile in your shell. You can also do it through the GUI here, in which case I said File, Compile Source, select the files and hit Compile. And then when you want to simulate, you have to tell it you want to simulate, and you have to give it the top level module you want to simulate, right? And so now you might say, what about the other modules? Don't worry, they'll get included, but that's done automatically. You just say simulate, like for example, in this case, the test bench, and all the things that are part of that test bench design will magically be sucked in through their file name, right? Through their module name, right? So you only have to tell it to simulate one file, even though you're really simulating multiple files.
That means they're all compiled and out there under the work.
Yeah, they go in the work library, and I don't know how this would work if, for example, if you put multiple modules in one file. I don't know if that would confuse it. I've never tried that, but I think this is built on the premise that you've compiled everything as a separate module file and named after the module. Okay, so then once you simulate it, you'll get basically it'll kind of reconfigure the GUI a little bit, and you'll see different things in here. There's a waveform window, and then there's this objects window. Now, one thing I want to point out here is that you'll notice over here, I know you can't read that in the back, I can't even read it from here, but over here on the left panel, there is a tree. This is the actual, this thing is cool. This is the design hierarchy. You see it here. It's in this tree structure. So you can drill down into whatever module you want by clicking into this hierarchy. And when you click on something over here, this objects window will automatically update with whatever's in that level of the hierarchy. And then once you have that, you can drag those in the waveform window and you can see what they are. So when you run the simulation, they'll be plotted, right?
Good for debugging?
Yes.
That's something you know the problem is.
This is for finding bugs. Yeah, that's what you're doing when you're doing this, finding bugs. And so here's an example of the design hierarchy. You can see this was, I had test bench. Under test bench, I had something called my adder. Under my adder, I had these smaller adders. This was an example I did years ago where I showed how to build a bigger adder from smaller adders, essentially. And there's the design. Okay, so I'm going to run through this kind of fast because the TAs will help you guys with this in the lab. That's what the lab is here for. One thing I want to mention here, though, is that QuestaSim uses the tickle language as a scripting tool. So you can do things through the GUI, and then you'll see the corresponding tickle command. And then you may find that you just want to write commands in the command window, or you can write a script, because there's really only a few commands you need to know. So there's restart that restarts the simulation. So whenever you change your design, you have to recompile it, right? And then you just restart. And when you restart the simulation, it will reload the new design that you've compiled, right? You don't have to restart the simulator. A lot of people restart the simulator. You don't need to do that. Restart will restart you to 0, times 0, and will reload the binaries. And then you can use the force command to force inputs to be something. They don't have to be inputs. You can force any signal, even if it's being driven by your code, your design. But usually use this for the signals. And so you can force A. Now, notice I'm using X dead beef. This is actually VHDL syntax. But you can also use Verilog syntax. Verilog syntax would be 32 apostrophe H dead beef, right? As opposed to X with quotes dead beef. But either way, it's very flexible with how you specify the values. Force op, in this case binary with quotes, force push to 1, and then run 100 advances the simulation by 100 time units, which is set up by default to be nanoseconds or picoseconds. It doesn't matter because we're not simulating logic delay. And then this command will set up a clock, right? So what I'm trying to say is really, there's only like 4 commands. There's restart, force, run. That's 3 commands. Where's the 4th one? That's it. No, it's just, there's 3. Reset, force, and run. So pretty much reset, force, run. There's also a command for adding things to the wave window. Sometimes you want to put those in your script, automatically add things to the wave window. So hold on a second. Let me plug in. Is there any questions about that? So if you create a script, you can just execute it by typing do and the name of the script, or you can do it through the GUI. You can go to File, Run Script. Yes?
Syntax or generating the clock signal, like how do we read through that?
I actually don't know. What I do is I always do this through the GUI rather, and I just paste it. I mean, obviously, this is the duty cycle 50, and this is the period 100. But these numbers, I think one of them is the initial. I don't know what these 3 are for, though. But yeah, I mean, 100, that's 100 units period and 50 duty cycle. But like I said, I do it through the GUI, initially. So here's an example of what you might have in a script file. So restart, force the clock, force reset, force push and pop. This was an example I used to do in this class where we created a stack memory in hardware. And so obviously I'm setting the push and pop inputs and data in, and then I run it. So this first run is designed to just reset, right? Set the inputs to 0 and give it a reset, a nice little one. If you type run without a number, it just runs for 100 by default. So run for 100 units to reset, and then I set reset to 0 and I start pushing and popping and stuff. So the idea is that you write this script and then you can validate that it's working by looking at the waveform, which is kind of a bad way to do it. It would be better if we had a way to automate this process, to check the outputs. But I don't actually know how to do that in Tcl, because normally the way you do that is through a test bench. You do that in Verilog, and I'll show you how to do that, because that's a requirement in Lab 2. So this is not a test bench. This is just like quick and dirty testing, basically, right? Where you can verify that things are working through the waveform. But if you want to have a self-checking mechanism where you write code that checks, I think you can do that in Tcl, but I've never done that because people use test benches for that. Okay. Okay, so that's the simulator. Now what about the synthesizer, Quartus? So that's just you type Quartus, it opens up Quartus. If you've taken 313, you're familiar with this one already. This is the GUI. You can load your project file. We're going to give you the project file. So if you download the project skeleton, we give it to you. You can open the project in the project skeleton, and that will be your starting point. You don't have to start from scratch, which, you know, usually if you start from scratch, you have to select which FPGA, you have to load in the pin mappings. We have all that stuff done for you, right? Now, what does the skeleton look like? I want to talk about that in a minute. So in the past, we would have everyone just open Quartus and do everything, you know, manually. We've automated this with a combination of files and a script. So if you download the skeleton, you'll see that there's actually already 3 files in there that have the SV extension. They're SystemVerilog files. There is a SymTop, a top, and a hex driver. SymTop is the top level that's used for simulation, and that is automatically what our script will simulate if you run the test bench design flow, okay? Then top is the top level file for synthesis, and hex driver is where you're going to put in your 7 segment decoder, which is the main objective of this lab. Right, you guys remember 7 segment decoders? Right, so you put 4 bits in as a hex value, and coming out you have 7 bits that are going to drive the little displays on the board, okay? So the way I tried to depict this, so SymTop has no inputs and outputs, because whenever you simulate a test bench, you don't actually want there to be any inputs or outputs on the top level of the simulation, because presumably you have code that's setting the inputs, and code that checks the outputs of the design under test, right? So the SymTop has 0, it's just a module with no IOs. But top has the IOs that are specifically set up for the board, so they're named appropriately. So you're going to see clock 50, clock 250, clock 350. Those are the 50 megahertz clocks coming in. We never use clock 2 and 3, I don't know what they're for, but we always just use clock 50 as our clock. So you can ignore those guys. Then there's key and switch. Key is the 4 buttons on the board, and switch are the 18 switches on the board. So those are all coming in. And then coming out, there's 18 red LEDs and 8 green LEDs. Now currently in our top file, we have some code in there already for you that will make the LEDs blink and shift back and forth. Why do we give that to you? Just so you can test to see if the hardware is working, right? And then there are 56 bits coming out for the hex decoder. So there's 8 hex digits of 7 bits each, and 8 times 7 is 56, but they're grouped into hex 0 through hex 7. Okay, and so I think the idea is that we want to take the switches and put each group of 4 bits of those switches into a hex decoder, and then have those connected to the hex output. So whatever you put on the switches should come out on the hex decoders. The problem is that there's 18 switches, which is not evenly divisible by 4. So first of all, what that means is that only 5 of the hex digits are actually going to work. Right? And the 5th one is only going to go from 0 to 3, because there's only 2 bits assigned to it. You guys, does it make sense? Right? Okay, so that's okay, but we still want to put all the hex drivers, even if we have some that are hardwired to 0, because once we put the CPU in there, the CPU will be able to set all the hex digits. Make sense? Okay? And so inside the SymTop, you'll put whatever testing code you want to use to test this. So the SymTop is going to manipulate these inputs as stimulus, and then it's going to check these outputs, right, with if statements and print errors if there's a mismatch, right? So you guys will have to put some code inside of SymTop, and you'll have to put code inside of the hex driver, and you'll have to instance the hex driver here in SymTop. All this is described in the lab sheet, by the way. I know I'm giving you a lot, but it's all documented, okay? And so the goal is basically to be able to test. There's certain minimal testing requirements that are described in the document. And when you demo this, we're just going to have you program the FPGA and hit the switches. And we want to be able to see 0 through F on each of the first 4 hex displays and 0 through 3 on the 5th hex display. Okay, and that'll be with the 18 switches. Okay, so then the script is called CSCE 611.sh, and you can run it with the test bench, program, or pack options. Program will program the FPGA, test bench runs the test bench. Both of these are without GUIs, by the way. You won't get a GUI. So if you need to debug something with the simulator, you're going to have to run QuestaSim by itself. And if you want to do something in Quartus and see the Quartus GUI, you got to run Quartus by itself. These are using the command line version of those tools, okay? And then pack is how you'll prepare your project for submission. If you don't use this and you just zip up your project directory, you won't be able to upload it to Dropbox because it'll be more than 25 megabytes because all of these tools generate a lot of intermediate, downstream files that we don't need to submit, okay? So pack is just going to compress just the upstream files that we need to see. And so you'll be able to submit it. And it also uses a naming convention, puts your name in there and stuff in the file name, okay? It's all in the lab sheet too. Okay, yeah, so that's not necessary. Okay, so that's all I've got for now. On Monday, I'll talk about the always statement, which is something you will need actually for this lab. You will need to understand the always statement and how to build test benches. So I haven't given you everything you need to know for lab 2 yet, but I will on Monday. In the meantime, if you want to get started early and start working with the tools, you can do that today.